All right, let's crack the code on one of the most reliable, most elegant sorting algorithms out there, merge sort. If you're getting ready for a tech interview, this is one you've absolutely got to know inside and out. So let's dive right in.
So let me ask you this. Have you ever just needed a sorting algorithm you can count on? One that doesn't have a secret bad day where it just slows to a crawl because the data was in the worst possible order?
Well, that right there is the unbreakable promise of merge sort. It's all about consistency, predictability, and that's exactly why it's such a huge deal in computer science.
And this is the part you really need to remember. Unlike some other big-name algorithms, merge sort's performance doesn't just fall off a cliff. It gives you that amazing, top-tier performance every single time. Doesn't matter if the data is almost sorted, totally backward, or just a random mess.
So how does it pull off this magic trick? It uses a super powerful strategy you'll see all over the place: divide and conquer. The idea is actually pretty simple. Take a big, messy problem, break it into smaller, way more manageable pieces, solve those little pieces, and then just combine the results.
This analogy is just perfect for the divide step. Imagine you've got a shuffled deck of cards. You split it in half. Then you split those halves, and you just keep going and going until all you have are little piles with just one card each. And hey, a pile with one card is already sorted, right?
Okay, so let's switch from cards to some actual numbers. Here's our starting point: a nice, simple, unsorted list.
So, what's the first move? We split it right down the middle. Now, instead of one problem, we have two smaller, much less scary problems to deal with.
And we just rinse and repeat. We apply that same logic over and over, splitting and splitting, until we literally can't split anymore. We're left with the most basic building blocks, these single-item lists. And just like that, the divide part is finished.
But okay, how do we get from all these tiny little lists back to one big, fully sorted list? Well, this is the conquer and combine part. And honestly, this is where the real magic happens. This is the merge step. So just imagine this situation. We've worked our way back up a bit, and now we have two smaller lists that are already sorted. The job now is to combine them into one single sorted list. So how do we do that efficiently? It's actually really simple. We use what's called a two-pointer approach. We just look at the first item in each list. Here, it's a 2 and a 1. Which one's smaller? The 1 is. So we grab it and pop it into our new result list.
And there we go. Our final sorted list is starting to take shape, starting with the number 1. And now the pointer for that right list just scoots over to the next element.
And we just do it again. We compare the two elements our pointers are looking at now, the 2 from the left and the 3 from the right. 2 is smaller, so it's up next.
And our result list just keeps on growing. You see the pattern, right? We just keep comparing the front elements, grabbing the smaller one, and moving that list's pointer along. We do this over and over until one of the lists is totally empty, and then we just tack on whatever's left from the other list. Simple as that.
Now hang on, here's a super important detail, especially for interviews. What happens if the numbers are equal? Well, the rule is simple. You always take the element from the left list first. This simple rule makes merge sort what we call a stable sort. It means if you have duplicate items, their original order is kept. And trust me, that's a huge deal in some situations.
Okay, so we know it works. We know it's clever. But how fast is it? And what's the catch? Let's talk performance.
This right here, this is the term you need to burn into your brain, n log n. And notice that funny little symbol theta? That means it's a tight bound. It's not just the worst case, it's what you get every single time. For sorting algorithms based on comparing items, this is the gold standard.
And it kind of just makes sense, doesn't it? The log n part, that comes from how many levels of splitting we have to do to get down to single elements. And the n part? Well, at each one of those levels, we have to look at all n elements to merge them back together. So we're doing n work, log n times.
This table sums it all up beautifully. Just look at the time complexity. It is a flat line of pure excellence. N log n doesn't matter if it's the best, average, or worst case scenario. But take a look at the space complexity. Theta of n. Ah, there's the trade-off.
And that leads us to the big caveat: memory. To do that magic merge step with arrays, you need a temporary holding area, a buffer, that's the same size as your input. That's O of n extra space. However, and this is a fantastic interview point, if you're sorting a linked list, you can do it with basically no extra space, just by cleverly rearranging the pointers. How cool is that?
So with all that in our back pocket, when do you actually reach for merge sort?
And why do interviewers love to ask about it so much?
The classic showdown is always against quicksort, and it really comes down to trade-offs. Merge sort gives you that stability and the guaranteed worst-case performance, which quicksort just can't promise. But on the other hand, quicksort is usually a bit faster in the real world, and you can do it in place for arrays, which saves all that extra memory.
So let's lock this in. These are your interview takeaways. 1. It is always stable. 2. It has a guaranteed nlog n runtime, no scary surprises. 3. It's perfect for external sorting. That's when your data is too massive to even fit in memory. 4. The linked list version is incredibly space efficient. And a little bonus fact for you, it was invented way back in 1945 by the absolute legend John von Neumann.
So there you have it. You're now ready for merge sort. But a good interview never stops there, does it? The follow-up question is everything. So think about it. Now that you know how it works, could you actually implement that linked list version using only a constant amount of extra space? That's your next challenge.